Let me go ahead and start the recording. I've had sessions where I spent literally the entire time going through, and then I realized I wasn't capturing my desktop audio, so it was like I was just speaking into the void on the recording, and that was it.
Oh boy.
So that was fun, yeah. And it was one of my better sessions back this past semester. I had 12 people all working together and collaborating, and then I realized afterwards, just like, God damn it. All right, let's go ahead and get the screen share going. Is it gonna work? There we go. Let me know if the quality is a bit off, but it should be fine. And then also, I mean, essentially, it's just pulling up the document that we're going to be, looking at is also in the session docs text channel. Are you comfortable? Are you comfortable with Discord?
Yeah, I got it. I have it up. I have the document up.
All right, sweet. So let's just go ahead and get going. First thing, what exactly is heat and energy? What are heat and energy? Like, give me your best interpretation.
Off the top of my head, give me a minute.
Yep.
Well, heat is the energy that flows from two different objects.
Okay.
And energy. Ooh, I cannot remember the full definition of energy.
How about
it's been a while to remember that.
More specifically, I don't need to the specific definition of what energy is, but in what context are we using energy right now? How does...
Would that be heat?
Would that be heat? So in what way? How is heat different from energy itself? Is it a specific type of energy? How does it work?
I guess we use energy for like common everyday use. We use energy to do things, and as we expel that energy, it creates heat.
Okay. I would think more specifically, heat is a form of energy flow that goes between objects when what happens? What has to happen for heat to flow between two objects?
They have to be connected.
And?
I'm trying to remember that one word. I don't think it's not equilibrium, but they have to be connected and... Oh, right. They have to have different temperatures.
Exactly. So we have to be not in an equilibrium, and then heat is going to flow, obviously, from the hotter object to the cooler object. At least that should be relatively straightforward. So what exactly is a specific heat capacity?
It's how much... I believe it's how much heat that the object can store?
Sort of? You're getting there. It has to do with how much heat, but it's not how much heat an object can store.
Can use? Or can expand? Something around there, I think.
Think about if you had a piece of metal, let's say a cast iron pan, and you had a plastic bowl. Are they going to take the same amount of energy, or like are they going to take the same amount of heat to increase a certain amount of temperature?
No.
So what is specific heat capacity in that context?
How much heat an object can take?
Not quite. I'm thinking more, it's the amount of heat required for an object to increase a certain... for the temperature of an object to increase a certain amount.
Okay.
Yeah, and so another thing I recommend... Oh, go ahead.
It's how much temperature it takes for the object to start heating up.
Exactly.
Okay.
And so what exactly does a higher heat capacity mean versus a lower heat capacity?
A higher heat capacity means they need a higher temperature in order to start rising, while a lower one needs a lower amount of temperature to start rising.
Not temperature.
Oh, heat.
Yeah. So, for example, let's say you have. We'll go back to the copper or the cast iron pan, but let's do water because I actually do know the specific heat of water off the top of my head. I have no clue what it is for plastic. So you have you have water and you have cast iron, and I'll tell you, the water has a higher heat capacity than the cast iron. What does that mean if we inject 1,000 joules of heat into the water versus 1,000 joules of heat into the cast iron, assuming they're the same mass?
And water has a higher heat capacitor, so it'll take more heat. Water will take more heat
To do what?
I guess in this case, probably to boil or to start rising in temperature.
So if the water were to increase, let's say 5 degrees from the, if water were to increase 5 degrees, would the cast iron increase more than 5 degrees or less than 5 degrees?
Oh, probably more.
Yeah, exactly. It's going to be more because it has a lower heat capacity. It takes less heat to do the same increase in temperature. And also, welcome guys, welcome Palumi, welcome Michelle. We're talking about specific heat capacities and sort of what they mean in the context of increasing and changing temperatures and heat flow. So let's go ahead and do one more thing. What exactly is latent heat? Roger, let's take a break here. And Michelle, Palumi, any of you want to explain what latent heat is or give your best description? Anyone? What is latent heat?
It's the heat that you have to add to undergo a phase transfer.
Is the heat you need to undergo a phase transfer? Can you sort of explain a bit more what that specifically is? What is a phase transfer or a phase change?
Also, it's when you're going from a particular substance to the next, like solid to liquid and liquid to gas. Latent heat has to do with solid to liquid or liquid to gas.
Is it the same for reverse?
No.
Why wouldn't it be the same?
Because the opposite is you're taking away heat in order for the particles to be closer together. So it's like endothermic.
So, but would it be the same amount of heat that you need to take away? For example.
Oh, yeah. It'll be the same amount of heat you need to take away, and then the same amount that it took you to add to it.
Exactly. Also, by the way, Michelle, I muted you. Let me know if you can just type in session text. There's just a lot of background noise on your end. Let me know if that's fixed. One more thing. Does the temperature of an object change when it's going through a phase transformation?
No, it doesn't change. It's the average kinetic. It's the kinetic energy that changes.
Yeah. Exactly. So let's go ahead so we've talked about specific heat capacities and latent heat and also just the concept of heat and energy. So let's go ahead and hop into an example problem. So we're going to have a 30-gram ice cube. Have our ice cube sitting here. Definitely a cube. Very accurate. And we're going to take it out of a negative 18 degrees Celsius freezer. We're going to place it on the countertop. It's going to slowly warm up and then eventually melt. How much energy did it take to heat the ice cube up to its melting point? And then also, how much energy did it take to melt the ice cube? Now, I believe, does he still give you the specific heat and latent heat of ice and water in your formula sheet? I'm curious about that because he gave this in the past. No, he does not. He changed it. Okay. We are going to...
I hope he changes back to where he does, because...
Well, it's just... this is the sort of thing where if you saw a problem like this on a quiz, he would give you the numbers right there. And you know the great thing? You have Google. So let's go ahead. Specific heat of ice. So we have 2.108 kilojoules per kilogram Kelvin. So essentially 2.1 joules per gram Kelvin. So let's write these down. C ice is equal to 2.1 joules per gram Kelvin. And the latent heat, fusion of ice, exactly. The heat fusion, we've got 300, so the latent heat, the fusion of the ice, so Li to water, so LIW, we'll call it, is going to be 334 joules per gram. Let's go ahead. Let's take like 5-6 minutes, and then we'll go over this. And if you have any questions, feel free to type in session text or just unmute your mics. All right, let's go through and talk about this problem. So, first things first, what do we need to know in order to solve this problem? What equations do we need to use? There's going to be two main equations we need to use for this problem. Michelle, were you going to say something?
Yes. I think it's the latent heat equation and the specific heat capacity equation.
Give me the specific heat equation. What is it?
It's Q equals MCAT.
Q is equal to MC delta T.
Delta T.
So what are each of these three things? What is Q?
Q is the heat.
Yep.
Energy.
Yep, it's the energy in the form of heat.
And then, M is the mass of the object.
Exactly.
C is the specific heat.
Exactly, it's specific heat.
And then T is the temperature change.
Exactly, specifically the change in temperature. Why isn't it just the temperature itself?
Because you're trying to measure like the because it's going through like a phase change, so the temperature is going to change.
Is this equation here talking about a phase change, or is this before the phase change? Before the phase change, exactly. But so why do we just have to worry about a change in temperature? Is it going to take more energy to, for example, increase the temperature of something from 1,000 degrees to 1,010 degrees than from 0 to 10 degrees? Which would take more energy?
Could you say that again?
So if we're taking, let's say we're boiling some water. We're just heating it up to boiling. We're going from 90 degrees up to the 100-degree boiling point. Would that take more energy than going from, let's say, 20 to 30 degrees?
Yes.
Would it?
Right. Because it's
No, because the 20 to 30 has a greater average temperature.
Well, you're right that it wouldn't be different, but it's more of we don't need to worry about the actual. If we're talking about changes in temperature, like heat flow and changing the temperature of an object, we don't need to worry about the starting temperature. For example, 10 degree or 20 degree, or in this case, 18 degree temperature change, no matter what the starting and ending temperatures are, is going to take the same amount of energy. It's just that there will already be a higher initial amount of energy for the 90 degree water versus the 20 degree water. So we have Q is equal to mc delta T. And so it's heat, mass, specific heat, change in temperature. What is the other equation? Roger, do you want to chime in?
Well, it will be the latent heat equation. I'm just trying to remember
exactly
what that was. Trying to look for it.
Do you have your equation sheet pulled up?
Yeah, I'm just no, that's phase change. I need the actual latent heat, I think. That's what I mean. I'm trying to find it. I don't know if I put it on.
I highly recommend having your formula sheet pulled up at pretty much all times in this class.
Well, I got the phase change, which is Q equals plus minus LM, I think.
I mean, would that not be it? Just, we have Q.
Oh, it is. There it is.
Q is equal to L, and in this case it's going to be LF because it's the latent heat of fusion. That just means it's solid to liquid or liquid to solid. Yeah. LM. And would it be
I just printed out the equation sheet, so I'm just putting on notes saying what these equations, like the names of them are as of right now.
So would it be plus or minus in this case?
We're heating it up to heating points. I'm guessing positive.
Mm-hmm. But
because you're adding heat into the object, so yeah,
exactly.
It should be positive.
Exactly. We're adding heat. We're going from a solid to a liquid. And so, as like we said before, Q is the heat, M is the mass, and then LF is just the latent heat of fusion. So it's this value up here. So for this problem, literally all we do is plug and chug. Substitute in our values for the mass, which is 30 grams. We have the specific heat of the ice, which is 2.1 joules per gram per degree Kelvin. And then we just multiply it by the change in temperature, 18 degrees. Anyone get a final value?
Would it be negative 18 degrees, by the way?
Would it be? What's negative 18 degrees?
Well, something that's very cold, but...
Michelle, you're going to say something?
Do you mean like, what do you mean by the question? Like in kelvins or?
Does it matter if we're working in Celsius or Kelvin here?
I don't think so.
Why is that?
Because Kelvin is... It's Kelvin in... Oh, go ahead, Michelle.
I think 1 degree Celsius is equivalent to 1 Kelvin.
Well, the change of 1 degree Kelvin is equivalent to 1 degree Celsius. But
okay.
yeah, they're literally like linear. If you were to graph temperatures Kelvin on a scale, if we want to do something like this, say Kelvin starts at 0 and goes up like this. Celsius is the exact same. It's just it's a certain distance below it exactly parallel. Does anyone know what this temperature difference is from Celsius to Kelvin?
$273.
Exactly, 273. So negative 273 Celsius is 0 Kelvin, absolute zero. But so because it's a change in temperature, it doesn't matter whether we use Kelvin or Celsius. In this case, we're starting at negative 18, we end at 0. So it's a total change of 18 degrees. So we should get a final value. Did anyone calculate a final value for the amount of heat?
I got 1,134 joules.
Yep, exactly. We'll call it about 1,100 joules. We're just going to round. And then what about part B? We have how much energy does it take to actually melt the cube? The same thing, right? We just plug and chug in our values. We have our 334 joules per gram times our 30-degree ice cube. How much energy did this take to melt the ice cube? Does anyone calculate a value?
I got around 10,000.
Yep, exactly. We'll call it 10,000 joules. Actually, just going to write 10 kilojoules. So it actually takes a lot more energy to actually force the ice through the phase change versus just getting it up to temperature. Does anyone have any questions about this so far?
Nope, not for me.
All right.
Whew.
Silence is golden, so let's go ahead and move on to the next problem. So we're gonna go ahead and make some orange juice, frozen orange juice ice cubes, because they're really tasty snacks. So we're gonna initially have the orange juice that we're gonna pull out of the freezer at 4 degrees Celsius. So let's say it takes about 400 joules. We need to take out 400 joules of energy from the orange juice to cool it to 0 degrees. So what would be the specific heat of the orange juice? 400 joules to cool 60 grams of orange juice to 0 degrees. And then if it took 250 joules to fully freeze the orange juice, what would be the latent heat of fusion of it? Let's go ahead, let's take 3 minutes, then we'll talk about this. All right, so let's go ahead and talk through this problem. We know the amount of energy it takes, or we need to take away from the orange juice in order to cool it, and the amount of energy we needed to take away to freeze it. So how do we calculate the specific heat and latent heat of our orange juice? What equations would we need to do this?
Well, we can use the specific heat equation. Q equals MC delta T.
Yep, so the same equation as above. So it's Q equals MC delta T. And then what about the latent heat?
That one I haven't hit yet.
For latent heat, you would use heat from liquid to solid equals negative latent heat of fusion times the mass.
Exactly. So it's the same equation as above here. It's just we throw the negative sign in because why do we need the negative sign here? So let me actually go ahead and so it's the same thing here. So it's Q is equal to MC delta T. And for B, it's Q is equal to negative LFM. Why do we need the negative sign here? As opposed to the positive sign up here.
Because you're losing heat. Sorry.
Exactly. We're losing heat. So, Palumi, did you want to say something?
Yeah, I was just gonna say because you're freezing as opposed to melting.
Yep. So, what does that mean about our value for Q? For example, our 250 joules. That would have to be negative, right?
That's a negative because it's exothermic. Yeah.
Exactly. So, because our Q value is negative, we need the negative sign over on this end to make everything work out and the equal sign to actually be valid. So, we have our two equations. What do? Well, let's just algebraically solve. So we have C is equal to Q.
1.66 for P.
Hmm?
Sorry, go on.
Yep. So it's just our C is equal to Q over M delta T. What is our change in temperature? How much? Oh, wait, go ahead.
I believe. I don't know why I have -4, but it's because I'm thinking of it was originally 4 degrees and then it's being cooled to 0.
Yep,
so
exactly.
I'm thinking so it should be 0 minus 4, so -4.
Yep, exactly. So then we have our 60 grams times -4. And our Q value, our 400 joules, would have to be negative, right? Because we're taking energy out.
Okay.
So the negative signs end up canceling out, and we still get a positive specific heat, and we thankfully don't break the laws of physics. You guys might accidentally break the laws of physics on about a dozen different occasions over the course of this class, but don't worry, it's probably just because you've missed a negative sign.
God, we broke the law of physics and now there's a black hole in our backyard.
Yep. So we have our 400 divided by 240. Anyone calculate a value of maybe somewhere around 5 over 3?
1.6.
Yep.
Like 1.6 continue.
Yeah, so about 1.7. Well, we'll call it 1.67. And what are our units for this specific heat? Well, let's think. What are our units of our three quantities here? Our Q is in joules, right?
Joules per gram Kelvin in this case?
Yep.
In this case, I think, yeah.
Gram Kelvin, or you could say gram degrees Celsius. It's all the same thing. We prefer to write Kelvin because you can't just say joules per gram C, like big C, because that's meaningless. You'd need to write the little degrees. But we want to only write one letter without the degree thing, so we write K, which means Kelvin. We don't need the degree sign.
Be lazy.
Exactly. We're min-maxing this crap. We ain't writing the frickin' degree sign, so we write a K instead of a C.
I just feel like there's so many problems they keep forgetting the degree that just say, screw it, let's call it K.
Yep. Alright, so then for the second part, we want to calculate our latent heat. So it's just LF is equal to negative Q over M, which is equal to negative 250 over our mass of 60 grams. Anyone calculate a value maybe a little above 4? Probably about, 4.2?
Yeah, 4.2.
Alright, we'll call it 4.2. I think it would be about 4.16 or something like that.
Yeah, it's 4.1. It's 4.16 continue.
We'll call it 4.17. 4.17, and then our units for the latent heat is, and once again we have joules up top per, we just have mass on the bottom, so it'd be joules per gram. Right?
Yeah.
So why do we not have to worry? Why is it just joules per gram? Why isn't it joules per gram Kelvin?
We're not worrying about the temperature in this case.
Because
because I honestly don't remember.
when we're going through a phase change, what happens with the temperature?
It's constant.
Exactly. Nothing. Nada. Doesn't do a damn thing. Stays at 0 degrees, and then once it's fully frozen, then it would continue to cool down further if it were to continue cooling. So, does anyone have any questions about this? We've talked about what specific heat and latent heat are. We've used them to calculate energies, and we've also done the reverse. We've used the energy to calculate the specific and latent heat. All right.
No question.
Once again, silence is golden. Not complaining about having no questions. Let's go ahead and hop into our last example problem. So we're going to have a 500 degree Celsius 2 kilogram copper rod. So I'm going to draw it as red because it is hot. We have I'm going to make it bigger. Boom. Here's our hot copper rod, 2 kilograms. And we are going to put it in contact in a closed environment with a 1 kilogram block of ice. We're going to make the ice this kind of like light bluish. Here's our 1 kilogram block of ice. Boom. I should have gone to school for art. Could have been doing commissions on Fiverr the last 4 years. So, the ice initially starts at negative 15 degrees Celsius, and the 2 kilogram copper rod is hot. It's 500 degrees Celsius. So we want to know what exactly is going to be the final equilibrium temperature for the system. And then with that final equilibrium temperature, is the ice still going to be solid, or is it going to become liquid? Or is it maybe even going to go past liquid and become a gas? Let's think about this. I'll give you guys 10 minutes to go over this, and 10 minutes to work on it, and then we'll go over it. I'll give you a hint. Think about breaking it into individual parts. Break the heat flow into different sections. That's the hint I'll give you. 10 minutes, then we'll go over this. All right, let's go ahead and talk through this problem. So there's a lot of things going on here, and the best way to do it is to sort of break it down step by step. Was anyone able to sort of get working on this and can sort of explain how they got started?
I believe one of the steps you had to do was Q total equals 0.
Okay. Yep.
Yeah, because it was in an isolated area, so you can assume that the heat for all substances is 0.
Exactly. So Q total equals 0, isolated area. That means all of the heat flow that, for example, leaves the copper rod is going to go into the block of ice / water vapor, depending on what phases it's at. So let's write that down. So we'll go delta Q is equal to 0 for every step. So what's the first thing that's going to happen here?
Figure out what's the Q of the rod and the Q of the ice?
Well, I'd say more specifically, because is the energy going to the energy is going to flow from the copper rod into the block of ice, and the ice is going to increase in temperature, right?
Yes.
Is it going to increase in temperature constantly up until whatever final temperature it reaches, or is it going to, or are there going to be parts where something different happens? Like, is there something special that maybe happens at 0 degrees Celsius?
At 0 degrees, the water would freeze, right?
Or, in this case, the water's already frozen. It's already ice.
So if it's beyond... Okay, so it would start doing the opposite then. Instead of freezing, it would be melting.
Exactly. So, I'd say, first of all, what we want to do is figure out how much energy is it going to take to increase the ice from negative 15 to 0 degrees. And we'll call that, we'll say Q1. So let's first of all figure out how much energy it's going to take the ice to go from negative 15 to 0. And then we figure out, okay, how much, so that energy came from the copper rod, how much did the copper rod decrease in temperature? And I suppose we should have also done this already, but the specific heat of copper is 0.385 joules per gram. So C is equal to 0.3, we'll call it 0.39 joules per gram Kelvin. And we already have the specific heat of ice. Does anyone know the specific heat of water?
Oh, that was the one thing I forgot to check.
It's about 4.2. Yeah, 4.18. We'll call it 4.2 joules per gram Kelvin. And we already have our specific heat of ice and the latent heat of fusion up here. And if we need it, we'll also search up the specific heat of water vapor. So Q1, right, we have our 1 kilogram block of ice times our specific heat, which is 2.1, times our 15 degree temperature increase. I'll actually pull out a calculator myself to do these. 2.1 times 15. We get about 31.5 joules, right? Is that right? Are we forgetting something? I did forget something, because it's 1,000 grams is the mass, because it's 1 kilogram. So we have 31.5 kilojoules. So that same amount of heat has to come from the copper rod, right? Total Q is equal to 0. So we'll call delta T1 for the copper rod is equal to Q1 over MC copper. Mass of the copper is 2,000 grams times specific heat is 0.39. The copper rod decreases by about 40 degrees. So 40.4, we would say negative 40.4 degrees Celsius. So what's the next step that's going to happen? What's the next step in this process? The ice has heated up to its melting point. Now it's going to melt, right? So we'll call this Q2 is equal to ml. We have our 1,000 grams. So we have our mass, our 1,000 grams, times our latent heat of fusion, which is 334. We'll call it 3.3. Got about, 3,300 or 3,300 joules, right? So how much is that going to change the temperature of our copper rod? So delta T2 is going to be our 3,300. We'll actually go ahead and add this to our energy from before. Sorry, it's not 3.3, it's 330. My bad. I'm bad at doing this. So it's 330,000 kilojoules. Go ahead and add that to our original amount here. So our total change in temperature of our copper rod now, so delta T 1, 2, we'll add them together, is going to be negative 463.5 degrees Celsius. So our copper rod is now only like 37 degrees. So I don't think our water is actually going to end up evaporating. I think it's going to stay liquid. So now what do we need to do for this last part? All we need to do now is...
we need to find the final temperature.
Exactly.
The equilibrium.
Exactly.
Of the final temperature.
Exactly. We just need to find our final equilibrium temperature. So how do we do that? So we'll call it Q water, going to equal Q copper. So it's 1,000 times 4.2, and this is, sorry, this should be kilo. Oh, it is 4.2 joules per gram. Yeah, okay. So 1,000 times 4.2. Hold up real quick. Copper. Yeah, copper specific heat is 0.385. Oh. So 1,000 times 4.2 times our change in temperature, which we'll call T final, is going to equal 2,000 times 0.385 times T final minus, or sorry, it would be our initial temperature, which is 500 minus the total change, which is 36.5 minus T final. Now we just solve for T final. And we can just do this in the calculator, or we can algebraically pull it out. And we should get a final temperature of about 5.7 to 5.7 degrees Celsius. Does anyone have any questions about this? Essentially, we broke down the process step by step. First had the ice heat up, then it melted, and then the copper and the water reached equilibrium. if there are no questions, I'm going to go ahead and wrap up the session for today. Sorry about rushing through this last little part because I have a session for Physics 121 in just a few minutes. But thanks guys for coming through. Hopefully this helped out a bit. Good luck on your quiz tomorrow. And I'll be hosting another session on tomorrow's material, same time on Thursday.
All right, thank you.
Yep.
Thank you.
And if you guys want to take a look at the recording, I've recorded the session. I'll upload it at some point, and you'll be able to find it in the Session VODs channel, or Session Videos channel.
Okay, thank you.
All right.
Okay.
All right,
Thanks,
have a nice
guys.
day.
See y'all.